Okay, thank you. Welcome. I'm glad I have another chance to remind you of some things that have been in the kernel for a while and some new stuff. So let me start with a discussion of internal parallelism. So the idea is that you want to use that parallelism that is available for our users by using parallel map, parallel table, stuff like that, also inside your own super function. So the idea is it should be as easy as just say parallelize of video generator. Now launch the kernels and it's now generating the video frames. Right. So what's required to make this work? So there is a registry. So if you have your own super function and you want to make it so that it can parallelize, then you have to write a handler that implements your algorithm, and then you can register that handler for your function. So this is the handler, and so this is your super function. And if you do that, then you don't really have to do a lot. So it's obviously hold first. And if you register it, and now if I do it, then it will automatically parallelize. So that's really all there is involved. The registration, the code inside parallelize before it calls your handler will take care of launching kernels, will take care of the options. So there are a number of options that you need to deal with, distributed contexts, the method that may give you an indication of whether you want coarse grain or fine-grained parallelism. And so the parallelize support code will pick up those options for you. And if you encounter a case of your function that cannot be parallelized, there's a standard message that you should issue. Now, another thing that could happen is, of course, say if you do run your super function inside another parallel computation, then obviously it doesn't nest, and so it will then just gracefully fail. So that is to make it easy to interface your function with parallelize. And so this is mainly for the record. I mean, I'll distribute, I'll send, make these notebooks available after the talk. So if you are interested in detail, then here's a discussion of how to handle these distributed context option examples of how to do it inside your code. I'm not going to talk about this in detail. So if you are thinking about parallelizing one of your functions, then this particular piece of information is for you. The other way to do it is to pass on the distributed context function to anything that you call internally. So there's another method option that is something that you can look at yourself if you have a way to divide your problem into fewer or larger pieces, or you can just pass it on to whatever parallel function you will call eventually. And there's a new progress reporting option that I haven't dealt with. I will do so for 13.3 so that it provides the correct way of feedback. You may have seen earlier when I showed you the video generator example that it had two progress dialogues, one from the video generator and one from parallelism. There should obviously be only one. So that's something I need to address. So there's, of course, a question, when do you register your parallel function? The register parallelize itself happens early in sysinit.m. So if you are in a packlet, you can just use it. But if your own function lives in startup directory, then there's no way to call something when you load MX files, right? There's just definitions. There's no initialization going on. So then you can put that register call into sysinit yourself. Now, there was and still is a supported way of doing your own parallelism without calling parallelize around it. There have been historically a number of functions that tried to do this, and they have committed various sins of for example, looking at kernel count, which doesn't work. Don't use kernels or any other parallel symbols, because that would trigger autoloading when it may not be desirable. There is a function that you can use. That's the one that is supported. Call that, and if it returns false, then you know that parallelism is not available, so don't try anything. If it returns true, you know that there are at least two kernels available. You can then look at kernel count and do whatever you like. Now, of course, as I said before, these parallel kernels are shared with users, so don't modify their state. And there is no way to launch a separate set of kernels for internal purposes at the moment. This is under consideration, but it's at the moment a rather low priority item because I have plenty of other things to do for the next two versions. Now, there is a kind of small distinction if you want to say, well, if parallelism is available, use it, but it's not important. Or you want to say, I want to try harder to use it, then there's this argument true or false, which signals whether or not it should actually launch kernels if none are running. So this is a supported way of checking for the availability of parallelism inside kernel code. So let me now talk about something new for 13.3 kernel configuration, because the overall picture is this, that well, let me show the, no, sorry, that will come later. So the idea is that these kernel configurations have evolved over, it's probably now almost 20 years, especially for remote kernels. SSH was very much in its infancy when this all started. And at that time, there was no network address translations. There were no firewalls, and everybody trusted everybody else. And so it was quite easy to launch kernels and make them connect back to your desktop. This has all changed, of course. Network address translation and firewall will prevent any backwards connections. So the old model that is still used by the front end, for example, of launching a kernel and then making it connect back, simply doesn't work anymore. But SSH has learned a lot more tricks, and in particular, SSH can now tunnel TCP connections through the one established connection. And so it is now possible to have those extra connections for the remote kernels to go all through one SSH tunnel. And so this was what I've been using for parallel computing for the last two versions or so. And this will be expanded. So the idea is that all of this kernel configuration machinery that I'm developing will later also be used by the front end to launch its notebook kernels. And so we will have one central place of managing local and remote kernels of various types. The first part of that is a user interface for configuring kernels. Now, these kernels may have lots of settings because, I mean, we have to support at least 3 different operating systems. We have to support different setups, different requirements for security and so on. So it's not something straightforward. So there will be a new function, kernel configuration edit, that takes a prototype kernel configuration, and let me show you. It will bring up a user interface. So this is a functional prototype. Don't look at how beautiful it is or not. That will go through proper design. And so this, for example, are all the properties that a local kernel may have. The most important one is, of course, the program to run. So if I want to run an old version, then I can change this. And when I say OK, it will return a new kernel configuration that is then immediately used inside remote evaluate. And so you can see that kernel was indeed version 13.2. So this is a convenient way of managing, handling all these different types of kernels. Now, these kernel configurations are immutable objects. They are just configuration information. The actual kernel that will be launched, which obviously will have internal state, that is the kernel object, which is not something that you have to manipulate yourself. And here you don't even see it because remote evaluate works by launching a kernel, performing a single evaluation, and then closing the kernel immediately. So you never see it. There are considerations to make this to support session kernels, so you can open remote kernel, then do a sequence of evaluations, and only close it at the end, similarly to how we support external sessions. Now, the big new piece will be a new tab in the system preferences. This is a screenshot from the 13.0 system preferences where the tabs were at the top, not at the left. And there is this parallel tab, which at the top has kind of general settings, but then below it had tabs for all types of kernels. So there's lightweight grid, which is the standard technology for grid mathematica. There is cluster integration, which is meant to interface with the highly sophisticated job management systems of supercomputers, local kernels, remote kernels, which are now called SSH kernels, and so on. So there was a limited GUI available for managing these kernels, but it was never very convenient, and especially the SSH kernels are now hopelessly outdated, as I explained before. So this got removed when we switched to the kernel configuration in 13.1, and it's now time to add something back. Because at the moment, and it's not too inconvenient, but at the moment you have to do the kernel configuration on the command line. So here I configure two kernels, one on the local machine and an SSH kernel. And if you want to use them by default, you can set an initialization value for your default kernels variable, and it will be permanently remembered. And every time you start a new session, these kernels will be available again. So at the moment, there is only this way of doing it, but I did write some tutorials, especially for the case of grid, because the grid kernels have a discovery feature. And that may be very nice because these grid servers advertise themselves just like the printers in your network, and you can see which ones are available and at the click of a button decide to use them. So I wanted to bring this back. And so there will be a new kernel configuration tab that replaces that parallel tab in the system preferences of 13.3. And another reason for doing that is that we now have a lot more use cases for kernels, parallel kernels. Obviously, that's how it all started. But then small side project which uses essentially the same technology is single remote evaluate kernels, where you can perform single evaluation on a remote kernel. And the very new thing that we plan is the notebook kernel support for, if you go into this menu, you see here the notebook kernel. And so the idea is that this menu will in the future be populated from entries that you configure here using this kernel configurator. So this is not yet in the prototype. So this is something that I'm working at locally. So here is a functional prototype of how this will look like. So the idea is you have a long list of every kernel that you ever looked at, and then you can click on these. And I mean, here, obviously, we don't need this test kernel. Say I have this SSH kernel. I can decide to edit it. And so now you see this is exactly the same edit dialog that I showed you earlier, except that for SSH kernels, there are still more configuration variables, for example, the SSH command, SSH arguments, and so on. So this is all rather complicated. The key file to use the remote operating systems. If it knows what the remote operating system is, it can provide meaningful defaults, and it just works a lot better. And port forwarding, that's that new feature I mentioned, and so on. So this is all rather complicated. But here is how you can define your kernels. And then you can go to this tab and say, I want to use these and this one for my default parallel kernels. And the same will happen for the notebook kernels and the default kernels for local evaluate and remote evaluate and so on. And there will also be a tab for managing running kernels, seeing which ones are running and kill them if they don't behave and so on. So this new dialog will come into the system preferences and make it possible to have one central place for managing all kernel configurations. And the result of your clicks in this table here will show up in the list of, well, this is the list of all kernels that appear here on the left-hand side. These are not being used otherwise, but of course, unless it just, no, it's okay. Default kernels are the kernels that you, excuse me. My voice is failing, so I hope I can make it through the end of that presentation. So the default kernels are the ones that are used for parallel computing. You can see if you open these blobs, then you can see how many will be launched for parallel computing. And the default local kernel and default remote kernel. Those are the ones that are used by default for remote evaluate and local evaluate. So this is the end of part 2. Are there any questions about the kernel configuration?
Have you guys looked at sort of AWS or Azure or something like that?
Well, the idea is that, I mean, these are all accessible through SSH. So the idea is that we could, in the future, provide subclasses of SSH kernels tailored to these remote environments. So it knows where to find the keys and so on. Might also interface with the management console to automatically launch instances. And we are, I mean, Jesse's work is already has produced a standard Amazon machine image that is already licensed to use the Wolfram kernel. So yes, in the future, the idea is that there would be separate entries for specialized SSH kernels that support these environments. This is all extensible. I mean, you can load new classes of kernels. I mean, at the moment, you see there are these types. There are local kernels, SSH cloud kernels, WSTP server, lightweight grid, and the test class. So these will be extensible. So we could provide, and also for cluster management. Now, cluster management has always been a little bit problematic because it has always been geared toward a very small number of very important customers, right? Those with big supercomputers in the basement. But it has never been actually reasonable to provide a package for supporting all of these systems just as a throw-in. I think this is more of a consulting project. So if you have a big customer who has a particular job management system and a supercomputer, then it should be easy in the future to provide a custom package that provides interface to that particular system. Okay, so let me go on. Let me close this document because for the next part of the presentation, I will have to switch to using version 13.2 because there are some things that are currently broken in the prototype, which I need to fix first. So there are no new features in what I'm talking about here. That's just a reminder of some of the good and bad uses of parallelism, because I get quite a number of bug reports or tech support requests for usually some horrible piece of user code saying, why doesn't it work? Why is it so slow? And so on. The answer is almost always the same. So let me talk a little bit about the efficiency of parallel computing and how to do it properly. First, one benefit of this new kernel configuration is this neat trick for launching parallel kernels. So up here, I just specify 3 machines that I want to use for this talk. And I can immediately use these as kernel configurations for remote evaluate. And I ask each of these machines for the number of processors that it has. And then I update the kernel configurations by the kernel count that I just found. So now you can see I have local kernel with 16. This machine is 24. And this baby here has 64 kernels. And so now I can just launch these kernels. So you see the feedback down here. And so now I have my 104 kernels available for the rest of this presentation. So here's a typical piece of code that I've seen many times. So you create some big blob of data. Here are 208 matrices, 400 by 400 matrices, taking up 266 megabytes. Then you do something like parallel table of the determinant of the ith such matrix. Oh yeah, it doesn't show the cell bracket, right? So you don't see that it's actually one here. So this takes, I mean, I've done it before, so you can see it's kind of, I should have deleted the output to keep the tension a little bit higher. So, okay, so this took 38 seconds. But of course, not every kernel needs all these matrices. In fact, each matrix is needed in only one of these kernels. And so what we just did is we distributed 266 megabytes of data to 104 kernels. And this happens sequentially, of course. There's the master kernel itself is sequential. It can only talk to one kernel at a time. So we spent a lot of time shuffling that data around. That is not really necessary. So the way to look at this is, first of all, I replace my table by a map. And then you can see that instead of mapping over the indices, you just map over the list itself. And so the list itself no longer appears inside the data here. So it will not be distributed. So if I do it like this, then it just takes 2 seconds and the result is exactly the same. Because in this example, I distributed a total of 200 gigabytes, not 100 times 200 gigabytes or megabytes, whatever it was. So this is the easy case, right? I mean, there are lots of examples essentially of this, distributing something that isn't really needed on all the remote kernels. There are other more subtle problems when you work with large amounts of data. So this goes back to about, I think it's more now, 2 years ago, when there was a lot of interest in combinators. So here I have 109,000 binary trees, essentially these expressions with combinators. So this thought is the combinator will apply a binary operation, and it has 43 megabytes. And so here I'm just doing a very simple computation. I do it efficiently, so I use the same idea as before. I don't distribute all the data at the same time, but it still takes a certain amount of time. It's now running. Now, the way to analyze this problem is that you never actually need all of the data at the same time. So the big insight here is that you don't generate all the data at the same time. Now, what we did earlier was that typical groupings of tuples, the tuples generates all possible combinations of these S's and K's, and then for each of those, the groupings generates all the binary trees. But this can really be thought of. So here's a simple example with just three terms. So if we untangle this, if we map the groupings over the tuples, we get the same thing. Different order with brackets. And now you can generate all of these sublists independently. So you shouldn't parallel map over the whole list, but over the intermediate tuples. There's still a lot of those. And this avoids generating all the data in the master kernel. So you only generate the tuples, and then you map the groupings and the function on the groupings over these, and you flatten and you get the same result as before. So this is typical for combinatorial generators. I mean, done to the extreme, you would actually come up with an iterator, like something like next permutation, right? So you don't need to, if you want to investigate permutations, there's no need to generate all of them if you look at them, each one in turn. So you shouldn't do that. So let me show you what the effect of this is. So here is the same computation as before, and it takes a lot less time. The result is obviously the same. So good dissection of your problems into manageable subproblems. So the main advantage of this approach is to minimize communication, and also the groupings are now computed on the parallel kernels. So these groupings are computed in parallel and not up front. I didn't even include that time earlier. It would have been even worse if I had done so. So this was one thing that is needs a lot of careful thought about organizing your data in a way that you minimize communication. But there's another way, and that is a way of making use of clever ways of generating your input data. So here's a simple example. I'd create a list 1 million elements which have, well, just floating point numbers, so it's 8 megabytes, not that horrible. And if I do that, that seems for some reason always the first thing people do. Parallel table of sign values. Now, if I do it like this, then it takes a lot less time. So what happened? Now here I pre-computed that list and mapped. This is essentially a map operation, right? It provides this list of data. And here I put the table generator inside the parallel table. And one feature that not everybody knows is that parallel table and parallelism are actually smart enough to recognize iterators inside. So instead of generating 1 million elements and then distributing them to the remote kernel, they symbolically dissect that table. So here's a simple example. If I have a table, 15 elements, so if I expand it first, then what happens inside parallelism, I have to take say if I only have two kernels, I take the first eight elements and then the second 8 elements, and I send each of these lists to one kernel. Now, if that's a million, then you can see that this takes quite a bit of time. But however, you could also have symbolically dissected table. Table from 1 to 15 is equivalent to a table from 1 to 8, and another table from 9 to 15. The result is exactly the same. But now I send these symbolic expressions to the kernels, and the expansion into the elements happens on the parallel subkernels. So you have essentially constant communication cost independent of the problem size. And this, of course, makes a lot of difference if you have a million elements or more. Now, of course, this particular problem is one you shouldn't even consider parallelizing, because if you do it sequentially, I mean, it takes the kernel a lot less time to compute the sign value than it takes it to send the sign command to a remote kernel and wait for the result. And people are very creative, so variants of this problem happen all the time, and they fill up my bug list and tech support questions. Now, another consideration is the output size. And so that now goes into a question of what is worth parallelizing. And one good example that is very good for parallelizing is select. Because select usually returns a lot less output than there is input. Here we have again 1 million elements, but only 29,000 of those actually satisfy that particular predicate. So this select is essentially searching large spaces of data, right? So you have 1 million elements and you try to find elements with particular properties and assume that there are only a few of those. So this is one particular example of a computation that parallelizes very well, especially if you combine it with the input feature of not expanding the range before you put it into parallelize. So this benefits from both. It does not expand that range. It dissects it symbolically, and it only receives a small amount of output. So this is a problem that parallelizes very well. Another example that parallelizes well is a reduction. When you don't collect individual results, but for example, the sum of all the results, then the amount of data sent back is very small and it all collapses down to one number. So these are the kind of problems that are easy, or that are worthwhile parallelizing. When you just look at the input and output size. Of course, another consideration is the amount of work to be done. So if you have a small number of problems that take a large amount of time, then that's another case that is worthwhile parallelizing. So all what I've discussed so far is under the heading of data parallelism. By data parallelism, I mean operations on long lists of data that essentially work one element at a time. And so these are easy to parallelize. Now, what about more general parallelization? Here is a general blueprint of easily parallelizing lots of different things. If you map a function onto something, then you can just compose that function with the parallel submit function. What that does is it generates parallel evaluations. And if you then let the scheduler loose, they will immediately evaluate and be replaced by the input. So this is kind of, whenever you apply function to things, you can easily parallelize that by just composing your function with parallel submit. Here is a nice example that I've asked for a lot. Parallel table only parallelizes along the outermost dimension of a table. So if you have a nested table and you want to parallelize along the innermost dimension, then you can just wrap the table argument with parallel submit. And when you do this, you get the fully parallelized table. Now, there's one slight problem here because these loop variables are obviously not available on the remote kernels. These are local variables. So you need to smuggle them into your held expression. This expression is, of course, not evaluated on the master kernel. And so the way to do this is by using this first argument. So the idea is the same as here. If you want to put the value of a variable into a held expression, like the variable I has value 42, how do I put the value of I inside here? You capture it in a function and you apply that function to an argument. And so that I here plays the same role as the I and J up here. So this is just a convenient way, so you don't have to do all of this all the time. So you specify those variables whose values should be inserted into the computation before it is sent to the remote kernels. So this is a very general paradigm for parallelizing. I mean, it works for inner, outer, and stuff like that. So parallel submit is an alternative to data parallelism. Here you don't issue one command that operates on a large list of data, but you actually specify which parts of the expression should be turned into evaluations on the parallel kernels. And then the wait all function schedules all of these unavailable kernels, and whenever all of them return, it returns the same result as the sequential version without the parallel submit here. Now we can do much more with this parallel submit wait all paradigm. So let me now talk about some advanced ways of setting up parallel computations. So now we're talking about concurrency and no longer about data parallelism. So the idea that I've used quite a bit and is searching large or even infinite spaces where you have few results, like you have a large search space and you search for interesting cases. And the search space is so large that it would be impossible to just, as we discussed before, generate all the data first and then do a parallel select. What happens if that operation, that computation crashes after 1 week? Then you've lost all the work. So you want to do it incrementally. So the idea is you write your own scheduling loop with parallel submit and wait one that just waits for one evaluation to finish, and then you write the big infinite loop around it. So the idea is you have a job queue that you should fill and then just wait for one result, and that is obviously non-deterministic. The first thing to return is the one you see. So let me restart my kernels here for these examples. Okay, there is a problem with one of my machines, so it will take a while. So let me discuss the code organization here. So the idea is that each kernel will run a loop that will repeatedly ask for a piece of work, then it will do the computation, then it will submit the result. So I'm working with a callback that is a shared function that will do the communication. And I have one global variable that will accumulate all the results, and I have one iterator that counts the input. So I'm here just using successive integers, 1, 2, 3, and so on, as my input parameter. And the predicate that I want to test is searching for Mersenne primes. So this is the predicate that is needed on the parallel kernels. And so here is my loop. So that's of course a lot of data. So let's untangle this. So this is the part that keeps me informed about the progress of that search loop. And then I have a checkerboard, so I can quit the computation when I'm tired of waiting. And then there is the big infinite search loop. And so this part fills the queue. So as long as the queue is not full, and by full queue, I mean I have at least as many elements as there are kernels, so all the kernels will be busy. I submit the predicate with the next input, and then if there is anything more to do, I have to wait. So this will invoke the scheduler, and as soon as the result is available, it receives the result. And if the result is successful, then I append it to the results. So let's see whether this actually works. So you see here in the front, this is the next input. So it's quite fast here with 100 kernels. And these are the Mersenne primes found so far. And you probably cannot hear it, but my workstation has now ramped up its fans, and it sounds as if it's about to lift off, because it's really, all the kernels are really busy, because some of these computations take a bit of time. And now I have to be brave and just hit Command period. And yeah, it worked. It's now resetting all the kernels, and now the computation is finished. So this is a blueprint for doing a potentially infinite search by providing your own search loop. So search loop means you submit tests to the remote kernels, and then you just wait for one, and then the loop repeats until you are tired of waiting. Now, it's of course very awkward to always have to write this piece of code. There's obviously a paradigm behind this. So let me show you how to organize that in a bit more modular way. So the alternative is, if I quickly go down here, I have now, instead of having the loop in the master kernel, I put the loops into the parallel subkernels. So the subkernels will ask for a piece of work to do, compute it, and then communicate the result using a shared function. And for efficiency reasons, I combine the two functions. So whenever a result is sent, it immediately receives the next piece of work. So this is the synchronization function. It's a shared function. That means it's essentially a callback. When this function is called on a parallel kernel, the function call itself will be sent to the master kernel where it is evaluated. So this gives me callbacks and thread safe manipulation of global variables. So the kernels will send the result and then receive the next piece of work to do. And there's also a variable that allows me to gracefully stop these kernels. If I set this global variable to true, then the kernels will receive $failed instead of the next input. And that makes them stop. You see, if the input is failed, they stop the infinite loop. So this code is now a lot more compact than the one before. And the main computation is, oh, sorry, I should have evaluated all of this, otherwise it's not going to work. So here's again my test, and here are my global variables. And so this is now the main loop, essentially just a parallel evaluate, where I run that worker loop on each kernel. And there's again some dynamic stuff around it. So if I run this, then I get the same thing as before. see here there is this stop button, and as soon as I hit, I will wait a little bit more. But as soon as I hit the stop button, you can then see here the number of kernels that have not finished yet, and it will gradually count down to 0. And the advantage of this is it doesn't have to use an interrupt. Interrupts are always a bit finicky, especially when you have remote kernels or strange communication protocols. So let me now push this button. Now it counts down, and eventually all the kernels will have stopped. So this is a very useful blueprint for organizing large, finite, or infinite searches. In fact, of course, we should really make that into a function. Let's just look at that last example, because it was really the last thing I wanted to show you. So there is this resource function, which incremental parallel select. It's in hindsight a little bit funny way of specifying the input. Now I've learned a lot more about iterators and so on, so I'll revise this function eventually. So it says test all integers starting with 1 for this particular predicate. So let's see whether this works. So now I'm just using local kernels. So this now uses the standard progress dialog, and there is an opener here because these results might be big, so you can hide them. But here they are small, so you can see. You see how many have been done, how many results have been found, and the elapsed time. Obviously, there's no estimate for the runtime because the search is infinite. So this is something I should revise, and because I'm now also working on some package for iterators proper, and obviously this first argument, this is really just an iterator, because every time you need a new element, it should just give you that new element. Let's try to stop this. Okay, so this worked. So what I talked about is, first I reminded you of some support code that already exists for doing parallelization in your own Wolfram language functions. And I gave you a preview of some of the upcoming features. We want to modernize the way kernels are configured and especially support modern features of SSH with tunneling. There's another good reason for doing that, because now for the last 2 or 3 years, Microsoft has an official version of OpenSSH for Windows, and it works quite nicely. It's the same arguments. It even accepts forward slashes in file names, and it supports all the standard SSH keys. So it's now almost as easy to use SSH from Windows as it is from macOS or from Linux. And the third topic was some observations about efficient and inefficient parallel programming, and a discussion of the more general queuing framework that allows you to formulate large or even infinite problems in an incremental way. Thank you.
Did we ever try to formulate data parallelism, where it might be out of core, like each kernel typically have, our kernels typically know about files, the file systems?
Yes. Now, we have never done it so far as to make it a standard part of parallelism, but one way obviously is if all the kernels have a shared file system, then one way, and I've done that myself on a Texas supercomputer with up to 1,000 cores, is instead of sending the data through masslink to these remote kernels, write the data to a WXF file and then tell all the kernels to read that file. And if the file system is up to its task on a supercomputer, so then this will be a lot faster because then all these subkernels can read the same file at the same time. So yes, that's something that would be worthwhile to turn into a standard feature for having an alternative way of distributing data to subkernel. I mean, essentially scatter and gather, right, using file-based transport. I've done that, but I've not, it's not, I mean, by hand, right? I mean, writing code, but maybe
Yeah.
we should probably have a standard way of doing that. So
Well, there's a lot of structured and unstructured data that gets collected
Mhm.
in huge log files that one needs to basically kind of just thrash through. There's a lot of tasks like that.
I mean, there is support for, what is it, file system map, or what is that function called that allows you to run code on each file map or file system. I forgot.
File system map and
File system map. And file system map, you can do parallelize of file system map. So that is already in place.
Yeah. No, I'm kind of thinking of there's so many obvious sort of data science Hadoop-like things, MapReduce-like things.
Yes, I mean MapReduce and those really require symmetric multiprocessing. And so all I'm doing here with parallel tools is strictly top-down, right? Master-slave parallelism. So you have always this bottleneck, and you have all these kernels that cannot talk to each other. And supporting OpenMPI would be a worthwhile thing to do, but that is a major thing, right?
Well, I'm sure we'll come back to it as we start to include more and more default parallelization, which we have to do.
Yes. No, I mean it would be. I mean, there's one way of. Normally, with OpenMPI, you issue an OpenMPI call, and it starts all those copies of your program on all the machines and arranges for the communication. But there's an alternative way of launching the programs independently and then making an OpenMPI call early in the program to hook them all up. So we could actually use our existing kernel binaries. They would simply have to call that OpenMPI synchronization call very early in their life, and then they could inherit all that symmetric communication. So if you have some good system programmer who understands this, then I think this is doable.
Charles Pugh wrote a long time ago. We did an MPI extension to our parallel programming. We did that 15 years ago or something.
No, we should dig this out again. I mean, this, as you said, I mean, this is now, everybody does this now.
Right. But I think that, many more people actually using it, actually thinking about, our problems as, what the real potential is, for parallelism. When the default assumption changes from 4 cores to 8 or 12 cores, things change. So then a factor of 4 improvement is, your best case is not as fantastic as a factor of 12 and other things. So
yes, I mean, one other problem is really if we start to do this. I mean, obviously, one as you said, one thing is to put it inside our internal algorithms. But if you want users to be able to do this, we have a lot of education to do, because I mean,
yes,
the typical code that gets submitted in tech support calls or bug reports, I mean, I just refuse to look at. I mean, it's.
So have you considered writing a MOOC?
Yeah, I mean, yes, but I mean, at the moment, I'm still very much tied up with all the actual programming work for deep planned extensions to the kernel thing. But yeah, I mean, if there is interest and if there's a commitment, then I would very much like to do this.
Great. Yeah, that's very much what we're in. All teams are very much engaged in teaching and learn and communicating what we do now. So there's a lot of book and course projects, books and MOOCs, as Shadi says. So it goes for this area too.
Yes. And compilation is another. If you combine parallelism with compilation, then you gain even more, I think, especially these search problems. And so, or using data types, right? Every time I do append to results, right? I shouldn't really do this. I should use a data type where append is a cheap operation, right?
Yeah, you mean a data structure?
Yes. Oh, yes, data structure. Yes.
Right. Any more questions?
Yeah, I have a question. Hi, this is Marcus. When we parallelize in image processing or video, we usually do multi-threading, and I'm sure we're not alone. And multi-threading commands and parallelization, like you have explained here, in a way counteract, because you already eat up all the threads, all the
Yes.
processes on a machine, at least if you're just on a single machine, essentially. So how do you optimize, or how shall we go about to make sure that we don't cannibalize each other and keep it functional?
Yes. If you can use multi-threading, then you're much better off, I think, using multi-threading than this kind of very heavy way.
What I'm trying to get at is, let's assume we have a multi-threaded command, and we use that in one of your parallelization schemes that essentially doesn't get us anywhere. And then the end user sits there and just wonders, did I do anything wrong? So I'm just wondering.
The way it's supposed to happen is that if you distribute your computation using my parallel tools, then those subkernels should have OMP threads set to 1. So they don't each spawn as many threads as they think they have available CPUs. There have been cases where this didn't work, and then the machine was completely overwhelmed.
Right. So I'm just wondering if it's worthwhile documenting if some function is multi-threaded in our kernel or not.
Yes. We should have the function web pages should say whether it's multi-threading, whether it can do parallelization, my kind of parallelization, and stuff like that. Yes, definitely. Also, we talked about. There is this parallelize, which is misnamed. Well, no, it's not misnamed. It's misunderstood. Because people think it's some magic wand that analyzes your code and turns it into beautiful and efficient parallelized code, but it's just a dispatcher for it. It knows what kind of things can parallelize. And there is now, it now lists all the cases there are. And I would like to see many more down here, especially the ones video generator and stuff like that use the extension registry. And so we should all document. Obviously it should also go the other way around. If you go to the documentation of table, I think, yeah, you see it's already in place. So there's a backlink here. So you see table can be parallelized. So you know that you have a parallel table available.
Another question related to this is currently our map, for example, our map function doesn't do multi-threading. It essentially just uses one thread to work through a function sequentially. I wonder if it's worthwhile considering a kind of an internal map version that does multi-threading, where we, in a way, sign responsible for the function that's being used in map, not to have inner states and stuff like that. Just for efficiency.
That is something for the compiler, right? Compiler does it.
Because expers, so our map uses expers for the function that uses ref counting, and we don't have a way of parallelizing ref counting now.
I think yes. You need to look at the compiler. The compiler can do multi-threading, and it can do all of that.
and there's a compiled map, which can be done in a compiled parallel map.
Okay, and that would be something. Okay.
Yes. I mean, if that, obviously, I mean, if your function doesn't really use expos, right, then you can compile it and then you can parallelize it. If it uses expos, then you cannot, well, you can compile it, but you will still have the kind of reference counting and everything.
Right. And Tom is working on something right now, which will make it so if you compile a function, okay, so the map function, then actually making the compiled map with that function, if you already have that function, would be much faster. So there's it's still, the compiler is still very slow to compile, but that would help with the speed a little bit.
Okay, thank you all very much. We can continue the discussion on L-kernel. I'm sure there will be many topics coming up on this.